right. We'll take attendance today. There's 2 attendance sheets. When it gets all the way to the end, pass it back forward so everybody gets a chance to sign it. Last time, we talked about self-replication. We talked about self-printing program for extra credit. We talked about generalized numbers towards the end. We said that beyond the complexes, there's quaternions, and there's octonions and sedentians. Lots of different number systems that generalize the complexes and ones that generalize those. And it gets pretty interesting. So if you never heard about these things, you can read about it from extra credit. I think it's just fascinating. So I mean, imagine if you went through life not knowing there's complex numbers, just real numbers. So a lot of people haven't heard about these other ones that are direct generalizations, including the surreals. The surreals generalize the reals, and then the surcomplexes generalize the complexes and the reals, and there's stuff beyond that. So any questions about any of that? And they all have practical applications, interestingly. The pigeonhole principle, we mentioned that. Let's just formally state it and discuss it a little bit more. Sometimes it's called the box principle. If you have too many objects, not enough boxes, some objects will double up, right? If you have too many pigeons and not enough pigeonholes, some pigeons will have to double up, right? It's pretty straightforward. It sounds simple, but it comes in and saves the day in interesting and non-trivial ways, this simple principle. So formally, we're saying that there's no injective or one-to-one function from a finite set to a smaller finite set, from a domain to a range. And more generally, if you have n objects and m containers, this principle says that at least one container must hold n over m rounded up to the nearest integer objects. And at least one container must have less than n over m. So at least one container must have more than n over m, and at least one must contain the floor of n over m. And that generalizes the n and n plus 1 case. So this generalizes to however many pigeons you have, not necessarily just one more than the number of holes. Any questions about that? Straightforward, right? Well, straightforward though it may be, it wasn't obvious at all that for a problem like this with the 5 points in the unit square, the pigeonhole principle comes in very handy. And the way it came in very handy is you partitioned the square into 4 subsquares. And when you did that, 2 points must fall in the same subsquare. It has no choice. And then they can't be further apart than the diagonal of this subsquare, which is half the diagonal of the square, which is square root of 2 over 2. And the problem is solved by the pigeonhole principle. Okay, and now that you have this idea, it's easy to see how it generalizes to other scenarios, right? So for example, another extra credit problem that we gave a couple of lectures ago is you have an equilateral triangle, and you have 5 points in this equilateral triangle, and it's the same question. Why can't every pair of points be further than half a unit apart in this 1 by 1 by 1 equilateral triangle? And the answer is because you can partition it by the pigeonhole principle very similarly to before. So if you partition it this way into 4 equilateral triangles, all equal size, at least 2 points fall in the same subtriangle. There's 4 subtriangles here. And therefore, it can't be more than a half apart if 2 points fall into that same subtriangle. And you can see how it generalizes to other shapes, and you can talk about hexagons, 7 points in a hexagon, partition into triangles, and you get a similar sharp result. How many can see the hexagon partitioned into 7? I guess, I guess it'll be six triangles, but 7 points in those 6 triangles. So 7 points in a hexagon. And you can even have more points in the same kind of configuration. So if you have, say, a square again, but instead of 5 points, you have 10 points instead of 5 points. In this case, partition it into what? If you have 10 points in the unit square, somebody yell out an answer. What's the strategy here? 9 squares. So partition it something like this, 9 equal squares, like a tic-tac-toe board. And then you have 9 tic-tac-toe subsquares, but 10 points, so 2 fall into the same. So that number, that parameter of how much apart can 2 points be at most is what in this case? Say something. Yeah, square root of 2 over 3, exactly. And now you can see how you can generalize it to more complicated figures, larger number of points, all because of the pigeonhole principle. It's a very powerful unifying technique here. Now, if you solve it without the pigeonhole principle, for the square, for 5 points, you may be correct. The proof will be a lot messier, and it won't generalize easily to all these other scenarios. You have to start from scratch and look for worst-case examples, and then it's not so obvious. So if I say a 1 by 1 square with 101 points in it, what would you do with that? So, but a pigeonhole principle, the answer is very obvious. So always look for unifying principles when you construct algorithms and proofs, for that matter. Okay, so any questions about any of that? All right, so what about this problem? Another extra credit problem. I said x to the x to the x to the x to the x, all the way out, infinite stack of x's is equal to 2. How many solved that? A few, okay. How many worked on that? Never mind, got it right. Okay, just a few also. The rest of you didn't think it was interesting, or didn't want to bother, or didn't have the time. That's all right. But again, let me remind you that problem solving is not a spectator sport. You got to practice it a lot to get better at it. I can only say it 17 times, but you got to do it. All right, so how would you solve this? Any thoughts? Yeah.
So we actually take the power item.
The exponent of the first x. Yeah, okay.
They're actually similar.
Yeah.
So turn about y squared.
Yeah, so you're saying that exponent of the first x, that quantity I circled in red, what is that equal to? It's equal to 2. How do we know it's equal to 2? Because it says so right there. Right? If you take an infinite ladder and chop off the first rung, you still have an infinite ladder, and it's exactly the same ladder that you had before. How many get that? All right. So that whole stack of x's is equal to 2. And therefore, you can rewrite it as x squared is equal to 2. I guess I'm repeating myself here. And therefore, x is a square root of 2. 1.414235. So it's almost unbelievable that if you take that quantity, 1.4, and keep raising it to powers of itself, you'll get 2. But it is true. And it has no choice of being true because this logic is foolproof. And interestingly, this kind of power tower converges for lots of other values, not just square root of 2. It converges for anything between e to the minus e and e to the 1 over e, which is roughly 0.06 to 1.444. And you can generalize this to complex numbers. So in the complex plane, if you do this computation for each one of those numbers in the complex plane, you get this result here, shown as a 3D surface, as a real number value of this exponentiation in a complex plane. And this is related to something called tetration. How many heard of tetration? Okay, good, a few of you. For the rest of you, tetration is a generalization of exponentiation. Just like exponentiation is a generalization of what? Multiplication. And multiplication is a generalization of what? Addition. And addition is a generalization of incrementation by 1. Incrementation. So you have incrementation. The next more powerful operator is addition. It's many incrementations in a row. The next more powerful operator is multiplication. It's many additions in a row. Right? The next more powerful operation is exponentiation. Is many multiplications in a row. And tetration is many exponentiations in a row. And it doesn't stop there. It keeps going. This sequence of more and more powerful operations. What's after tetration? Pentation. After that, hexation. Good. The force is strong in this one. The rest of you, Wikipedia for extra credit. Okay? And you don't have to believe me when I say that x is the square root of 2, you can go to Google Calculator and plug in square root of 2 raised to the square root of 2 raised to the square root of 2, type it about 20 or 30 times, and you'll see it's converging. That's not a proof. That's a sanity check. Okay. Any questions about that? It's always good to double check using a calculator what you know already to be true. Maybe one day you'll discover an error in Google Calculator and you'll become famous. Who knows? Or you'll discover some error in your logic and you'll just be better off for it and you'll think harder about solving the problem. Either way, it's good. All right, so let's talk about algorithms in general. Before an algorithm is efficient, it must be correct. If it's incorrect, it doesn't matter how efficient it is. I have a very incorrect but efficient time to tell algorithm to tell the time anywhere, any place. Just say it's midnight, and you'll be right twice a day. So it's very efficient, but it's incorrect. So an algorithm must be correct first before you even worry about efficiency. I'm just stating the obvious, right? And it's not trivial to say that an algorithm even exists. Never mind that you know what it is. Because we already saw that some algorithms don't exist, like for the halting problem, there is no algorithm. So not only you don't have an algorithm for the halting problem, not only I don't, a deity won't either because it doesn't exist. Just like the integer between a quarter and a third, it ain't there. So it's a not trivial statement to say before you're trying to make something efficient, make sure it first exists. And of course, next, make sure you know what it is. And then you make it efficient, if you can. And by efficiency, we usually mean time. But don't forget space, because space is also very important. In fact, it's more important than time. If I give you any number of, if I give you any finite quantity of a resource, let's say 1,000 units of some resource, and I say, do you want to pick space or time as a bound? If I bound you by 1,000 units of something, do you want to be bounded by time or by space? And if one is bounded, the other, it doesn't matter how much you use. You can use it to your heart's content. So you want to be bounded by space or by time to get more value for your buck. I hear time. How many say time? How many say space? All righty. Split vote. That means I asked an interesting question. So what do you say? Anybody want to argue why? Space or time? If I'm giving you a limit, do you want to limit it by 1,000 units of time or 1,000 units of space? If you're limited by one, you're not limited in the other. What do you say?
I'd rather be limited by time because I can infinitely parallelize if I have unlimited space.
So we're not talking about infinite parallelism here. You have a single processor. So I'm not allowing infinite parallelism, because that would be a nice trick too. But let's just stick with a single processor. That's a more subtle question. What happens if you have infinite parallelism or even non-determinism? That's a much more deeper and subtle question. Yeah.
Well, if you're limited by space, a lot of complex operations won't fit into whatever you're working with.
You're saying if you're limited by space, a lot of complex operations won't fit into the space, into the limited space that you're allotted. Okay. What else? Yeah. Yeah, your space bound is your time bound as well. Your time bound is if I say you can use this much space, and you actually try to use it by touching each memory location, by writing or reading from any amount of memory locations in that space, how much time have you used? You've used that much time, right? It takes you 1,000 units of time to touch or modify 1,000 units of space, right? You can't modify the entire space or use the entire space in any meaningful way if you don't have time to use it. How many get that? So your space bound and your time bound are kind of related. You can't use more space than you have time to use. But if you have an amount of space that you can use, and that's your limit, and you can use as much time as you want, you can spend a lot of time using that limited space. How many get that? Yeah. So you're better off accepting a space limitation than a time limitation, given that the other is free. Another way of saying it, space is reusable, time is not reusable. They're not symmetric. You can reuse a bunch of space over and over and over again. You cannot use time over and over and over again. Your time is limited. And that's almost a philosophical question or philosophical statement or outlook. It's true in life. It's true in the universe. Right? You can reuse the same space over and over and over again and get more and more value by shuffling it around, erasing it, reusing it, and so on. But you spend 1 second or 1 minute or 1 hour or 1 year and it's gone forever. You cannot reuse that. Okay, any questions about that? So always keep it in mind, and in algorithms, the time complexity and space complexity are related. Right? The space complexity will always be less or equal to the time, even if all you're doing is touching space at every moment of your running of the algorithm. It reminds me of this joke. This guy releases a genie from a bottle, and the genie says you can have one of two things: infinite money or infinite wisdom. Take your pick. And the guy thinks about it, feels real erudite and lofty and philosophical. And he says, "Okay, I'll take the infinite wisdom." And the genie goes boom, and he has immediately becoming infinitely wise. This guy. He thinks for a couple seconds, says, "Damn, I should have taken the money." So, any questions about that? And when we analyze algorithms, usually we go for the worst case. We don't care what happens in the best case or in a specific case or in some subclass of cases that's very esoteric. We look at the worst case analysis. And sometimes we will look at the average case too, because that's important. And Don Knuth came up with this kind of notion that you should look at the worst case and talk about the asymptotic growth, big O and omega and theta and that kind of thing. So the high order term of the growth rate of the function of the resource usage that you consume while you compute, whether it's time, whether it's space, or whether it's other things. Okay, so upper bounds. But before we even say that, I said whatever resource you consume. So we talked about time and space, but I don't want you to get the false impression that time and space is the only resources that you try to minimize or optimize while you compute. What other resources might you try to minimize or optimize while you compute, besides time and space?
Fairness.
Fairness, okay. Fair enough. What else? Power, yeah, power used. Why is power important these days more and more? Smartphones, any portable device, it's a finite battery, even electric cars. You want to minimize the power you use, not necessarily the time or the space, because you might run out of power way before you run out of time or space, especially when you're watching videos on your smartphone. What else? Name 10 other things. The length of the code, okay. You may want to minimize the length of the program or the size of the program or the number of lines in the code. Okay, fair enough. Or what else? Privacy. Good. That's kind of an abstract one, but yeah, you want to maybe maximize the privacy. What else? When you write code or produce programs or design algorithms, what else might you want to optimize or minimize besides all these 7 things that we already mentioned? Complexity in terms of how complicated the code is, how convoluted, hard to construct, hard to explain, hard to follow, hard to debug, or even program in the first place. You may want to optimize programmer time, because you have to pay an army of programmers, to write the next OS, and you want to minimize the cost, the physical monetary cost of producing a piece of code. And by the way, an operating system that Microsoft produces these days is about 100 million lines of code. And it takes about 1,000 people to work on it for about 5 years. That's 1,000 person years to produce an operating system. That's a lot of time and effort and a lot of money. We're talking about $1 billion or more, yeah. Scalability, yeah. You may want to optimize scalability, make sure it is scalable. What else? User? Reuse, yeah. Software reuse, yeah, absolutely. If you're running over a network, what might you want to try to minimize or optimize? Messages or bandwidth that the thing needs across a network, right? Disk accesses, for example, between processor and disk, you want to maybe minimize that because memory accesses are much faster. How much faster is memory like RAM than disk? Give me an order of magnitude type approximation. How many zeros are we talking about? How much faster is memory versus disk? I hear 100? 10? I hear 100, I hear 10. I hear 1,000. Anybody want to say 10,000?
So what kind of disk are you talking about? Like an NVMe or
I'm talking about a hard drive,
hard?
spinning hard drive. Yeah, like if I go for a random byte on a hard drive, what's the access time like? Again, I'm not asking for exact figures. I'm not even saying which hard drive. Seagate, Western Digital, IBM, Toshiba, they're mostly the same.
200 megabytes per second.
Yeah, but the access time to fetch a single byte, not the streaming rate while I'm actually know what I'm getting. I want to go to a random place on the disk and fetch a byte, or a page or a sector, but how long does that take, this operation, for a random place on the disk? Well, I guess I'm asking more and more interesting questions because it's a room full of computer scientists, right? And most of you are graduate students, and many of you have actually worked as programmers, presumably for companies, and you're not sure what the disk I/O seek rate is? How did you keep your job? Hundreds of microseconds? Hundreds of microseconds? Okay, we're getting closer. How many times per second can you access random things on a drive? How many times per second? Let me ask the other question first. How many times per second can you access random things in RAM, random access memory, solid state transistor memory? When you buy a computer, right, it tells you what the speed of the memory is typically, right? The DDR, the RAM, how many megahertz or gigahertz? You know, how many megahertz are we talking about for a RAM these days? It's about a few hundred million, hertz. It's a few hundred megahertz, maybe 800, maybe 1200. Like, roughly, it's a gigahertz. Let's call it round number, right? That means you can access memory about 1 billion times per second. Right? How many sort of agree with that as a ballpark figure? RAM speed is in the order of a gigahertz, maybe 800 megahertz, maybe a gigahertz 0.2 or 1.2. Anyway, roughly a gigahertz RAM speed. All right. How about disk?
So typical hard drive is like 7,200 RPM or 5,000 RPMs. So
Yes.
that would be the frequency of a mechanical hard drive. That would be how fast you can get from worst case one point to another point.
Yeah. So one way to guesstimate it is how fast does a hard drive spin, typically? How many RPM, roughly? 5,400 or 7,200. Really fast one is 15,000, but it's not millions. So to find a random bit on a hard drive, on average, it has to spin how many times until that bit is right under your read-write head? About half a turn. And if it's spinning at 5,000 RPM, we're talking about, almost a millisecond, right? And that's not all. Let me back off. Don't want to be presumptuous. How many know how a hard drive works even? Okay. Really? Only a third of you? All right. Let me ask again. Maybe you didn't hear the question. How many know what a disk drive is? Okay. I'm relieved. All right. How many know what's inside, how it works roughly in general principles? Not exactly. Okay, good. So I was worried there for a second. Okay. So again, seek time on a hard drive roughly is what? Given all this discussion. Remember, the read-write head has to move too. It's not just a platter that has to spin to the right angle, the read-write head has to move and be placed right over it to the right track. It's a few milliseconds, like 5, 10, 15 milliseconds. It's a few milliseconds. How many times per second can you do something that takes a few milliseconds, like say 10 milliseconds each? How many times per second can you do that thing? About 100. All right. So you can access disk randomly about 100 times in 1 second on a very good day when nothing else is interfering with that. All right, back to RAM. RAM was 1 billion times a second. Hard drive, you just told me it's 100 times a second. How much faster is 1 billion than 100? How many zeros difference is that? 7 zeros. How big is 7 zeros in terms of number? That's 10 million times. Bottom line is RAM is 10 million times faster than disk. Okay? You follow? So when you optimize stuff doing algorithms, you may want to minimize disk accesses very aggressively, even if you have to spend a lot of RAM time doing that, and keep things memory resident, and not just page them in and out of disk every time you need something. Very, very important. How many have thought about that while you were programming, at least sometimes? Okay, good, a few of you. The rest of you, start doing that, and your code will get a lot more efficient and scalable. 10 million times difference. You can touch RAM 10 million times for the cost of touching disk once. So imagine the optimization you can do there. Question? Assuming what? We're not assuming burst necessarily, but you need to keep in mind all the specifics. You know, if it's like burst mode, or you want to fetch a lot of things that are contiguous on the disk, you know, it changes the calculus a little bit. But it's still a huge discrepancy between RAM and disk. Okay, and yeah, RAM is more expensive, and now you know why we go for expensive RAM and not inexpensive disk for most of our memory that we can afford to have. Because you know, it's more expensive, but it's much faster, so we prefer it. If they were the same cost, disks would never have been invented or never used for many decades. Right? We'd just go for RAM. And of course, now the prices of RAM has dropped so much that they're beginning to replace disks altogether, and a lot of your computers right now don't even have a drive in them. A hard drive is spinning drive. Do you have an SSD, solid state disk, which is just a bunch of RAM, static RAM that can keep the value even while the machine is turned off? That's actually important. Okay, so when you design algorithms, you have to keep in mind all these other factors, you know, power and, you know, complexity, the size of the code, programming time and expense, messages passed over the internet, bandwidth, disk versus RAM speeds, and a whole bunch of other things, ideally, and not just blindly minimize time and walk away in victory. That's too naive of an approach. Okay, so bounds, upper bounds, big O. F is big O of G if G dominates F from some point on forward. So this function in red, F, is dominated by G if there exists some constant, some positive constants, C and K, such that F of n is strictly smaller than C of times G of n for all n bigger than K. From some threshold forward, this threshold, we call it K here in this definition, G better win. And then G is an upper bound for F. And notice it doesn't have to be strictly higher. It's higher modulo a constant. So this notation ignores a constant. As long as there is a constant that makes this true, this constant being C, that's okay. Strictly speaking, without that constant, or more precisely, when that constant is equal to 1, they can flip. But if that constant is 2 or 3 or 1.2 or even 10 or even a million, and this is true, F is still big O of G. That's important to understand. This notation hides constants. That's both a bug and a feature of this notation. Usually we wanted to hide the constant and we want to ignore the constant because we're just interested in the magnitude of the growth, the exponent of the polynomial that is driving this explosive growth, or the exponential in some cases, or even worse. But in practice, we often want to keep track of the constant, make sure it's not too large. And we'll come back to this issue and give examples of very dramatic examples of this. Okay. Strictly speaking, big O is actually a set. It's not a single function. So big O of G of n is all the functions f that satisfy this criteria, that f is big O of G. So it's a class, infinite class of functions, and it's not even a countable set, it's an uncountable set. How many know what I'm talking about there or knew that from before? If not, don't worry too much about that. I'm just bringing it to your attention. The type of object that big O is a class of functions. It's not a unique function or even a small set of functions. It's an infinite set of functions. It's an uncountable set, and it's all the functions. So really, this equal sign is a misnomer. It should be what? Instead of an equal sign in this definition, this equal sign should strictly be correctly stated as what? Set membership. Okay. So I just wanted you to at least hear it once if you never heard it before, this nuance. And we just say f of n is big O of G of n, and here's some examples. Linear is big O of a quadratic, right? Ignoring constants. And 33 plus 17, that's big O of n, right? They're both linear. N to the 8 plus n to the 7 is big O of n to the 12. That's pretty clear, right? N to the 100 is big O of 2 to the n. That's not as obvious, because n to the 100 grows really fast. But 2 to the n grows even faster beyond a certain point and going forward, right? Because if n is 2, 2 to the 100 is 2 to the 100, but 2 to the 2 is still only 4. So why is 2 to the 100 big O of 4? Well, from some point forward, it'll be true. We are ignoring the left tail of this relationship, just so you understand. And 213 is big O of 1. Any constant is big O of itself, and particularly of 1, because they differ only by a constant. In this case, a constant is 213. That 1 is different than 213. But strictly speaking, that's true. Okay, any questions about this? So that's, again, most of you have seen this before, but I'm just stating a few subtleties and the definitions, so those of you who haven't seen it, that's what it is. F is omega of G of n if it's flipped. If G of n is big O of f of n, then f of n is omega of G of n. So now this definition is now very simple because it just uses the previous definition by reference. How many get that? So this is a lower bound. So f of n is lower bounded by G of n, and it looks like this. Right? Another way of saying it is that G of n over f of n exists. But that's usually not the functional definition that we use and intuit about. It's usually kind of the asymptotic growth, pure and simple. That too is, of course, a set of functions, because now this definition boils down or reduces to the definition of the other one. Anybody not signed the attendance sheet? And if not, looks okay. And we say f of n is omega of G of n, or big omega of G of n. Here are some examples. 100n is omega of n. This 33n plus 17 is omega of log of n. Why? Because log n grows much more slowly than a linear. Logarithmic growth is smaller than a linear growth, or any polynomial growth for that matter, even lower than n to the 1/2 or n to the 3rd. Log is less than the cube root or the square root, generally, in terms of asymptotics. And n to the 8th minus n to the 7 is omega of n to the 8th, and so on. A constant grows less than a reciprocal, because the reciprocal vanishes to 0, and that's a lower bound to any constant, modulo a constant, some other constant embedded in the notation. And any constant is lower bounded by 1, or any other constant for that matter. Okay, any questions about this? Yeah. What about the upper bound? Well, so f of n is lower bounded by g of n. That means g of n is below f of n. See, the other definition on the previous slide was the opposite. F of n was upper bounded by g of n, so f of n was below g of n. And here, g of n is below f of n. They just flipped. That's all. So these definitions are kind of symmetric. And that's why we can state one in terms of the other, pure and simple. We could have taken all this written on the previous slide, written it here, and then just flip the equals, the inequalities, and so on. But it's easier to just state it in terms of the other once you understand the other. Okay. That's called calling a subroutine. In mathematics, when you call a subroutine, what is that called? What is that called in mathematics? A lemma. Right? A theorem uses a bunch of lemmas. Those are subroutines, logical subroutines. Anyway, it's kind of a mathematical joke, pun. And that gives us to the third definition. F of n is theta of g of n if it's both big O of g of n and omega of g of n simultaneously. Another way of saying it, if each one is big O of the other, they're both theta of one another. Okay, so these are equivalent, if and only if symbol right there. And that's the same as saying that the limit of each fraction, either this way or that way, both exist. They both converge. And the picture looks very similar to previous pictures, except f of n is both upper bounded and lower bounded by g of n, and the two constants can be different, but they still exist. So f of n is sandwiched between two g's, and it's really the same g with possibly different constants. Or they can even be the same constant in some cases. So that's an exact bound, right? So 99n is theta of n. N plus log n is also theta of n. Tell me why this is true. Why is n plus log n theta of n? Log n is bigger than a constant. So why, when you add log n to n, you get an exact bound of n?
Because as you approach infinity, the log of n, because it's going so much more slowly, kind of vanishes.
Yeah, but it always adds.
But when we're looking at whether or not the limits exist,
Mm-hmm.
you don't consider something as
Yeah, sure. Log n is so much smaller, but why doesn't it increase the asymptotic?
because your asymptotic is always bounded by the fastest growing.
Why? That's what I'm asking.
Because we're trying to measure the order of magnitude at which it grows. We're not trying to measure the exact speed.
Yeah, but everything you're saying is true. But prove it to me. Yeah, this thing here is smaller than n, right? So this thing here is smaller than what? Than 2n. So this thing here is bigger than n, right? And smaller than 2n. So it's sandwiched between n and 2n. But it's the same function n modulo two constants. The constant in the first is 1. The constant on the second is 2. And that's always sandwiched between those two. And that's why it's order n. And that's why the dominant term is the most important term. That's why the highest order term dominates, because of this kind of reasoning. It's not a freebie of logic. You have to argue it like this. But once you argue it like this a few times, you get the hang of it, and now you can just ignore the lower order terms and just focus on the higher order term, and that's what we do. But don't write off all that logic. It's necessary to prove it from first principles. And that's why we can say n to the 8 minus n to the 7 is n to the 8, theta n to the 8, because you can sandwich it between n to the 8 and half of n to the 8. You see? And so on. N squared plus a cosine is theta of n squared. Explain that one to me. N squared plus a cosine. A cosine keeps going up and down. So why don't we have to? Why shouldn't we add some term to here? Or sometimes it's cosine. Sometimes it's negative. Sometimes positive. So it sometimes adds to the n squared. Sometimes subtracts from the n squared. So how can we say it's exactly n squared? Yeah, it's bounded between plus and minus 1, the cosine. So this whole expression is always bigger than n squared minus 1. It's always smaller than n squared plus 1, and therefore it's always n squared. Because the n squared minus 1, n squared plus 1 is still bounded by n squared over 2 and 2n squared, say. And there you go again. We're sandwiching it tightly between two expressions involving only n squared, and it satisfies this criteria. And that's why. And you can't just say, well, this is smaller than that. We can just ignore it, and that's a proof. It's an intuition, and it's correct, but by itself, it's not a proof. Okay. Any other questions? Any constant is state of any other constant. And we'll come back to this again and again and use it and argue about it and make statements about asymptotic growths. So it's important that you wrap your mind very tightly around these concepts. Okay? And there's a whole parallel set of loose bounds. So f of n is little o, not big O, but little o of g of n, if it's big O of g of n, but not omega of g of n. In other words, it's bounded from above by this function. F is bounded from above by g, but not bounded from below by g. Okay, so I'll just flash through some examples and the definition. It means g bounds it from above, but not from below. Okay, so another way of saying it is it's big O of g of n. So f of n is little o of g of n if it's big O of g of n, but not omega of g of n. Okay. So again, we're reverting or using the previous definitions as subroutines, as lemmas here, to define this. So for example, n to the sixth is little o of n to the 6.01. Right. And by the way, the omega, the little omega is a similar notion here. Okay. So another way to think about this intuitively is you can think about big O as a less than or equal to, asymptotically speaking, functionally speaking. So little o will be what in this analogy? Strictly less than. Okay. And you can think about omega as being greater than or equal to, and little omega is therefore what? Just less than strictly, but not equal to. So little o and little omega are less than and greater than respectively, whereas big O and big omega are less than or equal to, or greater than or equal to, respectively also. So it's not strict inequality, it's non-strict inequality. It allows for things to be strictly less, but not equal to. So this is not used as often as the other two. Let me just say that right now. Usually we talk about big O and big omega and big theta, and not so much the little o and the little omegas. Although occasionally we'll use it and say that as well, just not as often. Okay, any questions about any of this? Okay. So some growth laws you can prove pretty easily, pretty immediately. If f of n is big O of g of n, and if you have f1 is big O of g1 and f2 is big O of g2, then their sum is big O of the max of the two bounds, right? It's not an obvious, it's not an axiom, it's not completely obvious, but you can prove it pretty easily, right? So for example, if you're running two pieces of code, and one has the complexity of f1, one has the complexity of f2 in terms of time or space, then if you run them both back to back, one after the other, the total complexity of running them both as subroutines in a larger program will be the maximum of the two complexities. How many believe that, or at least can see that intuitively? Yeah, right. The one that takes more time and more space will dominate the ones that take less and make it almost irrelevant in terms of its usage of resources, and then we just revert to the usage of the more expensive one in time or space, and that's the dominant term, and the other one is almost free at that point. And in a more intuitive setting in everyday life, if you have two tasks to do, and one takes an hour and one only takes a minute, together they still take about an hour. Right? The minute is almost washed away by the much longer task that takes an hour. That's what we're talking about here. Okay. When you do the product of two functions, the product of two functions grows asymptotically as the product of the two bounds. Then it's not free. Okay. Or it's not as cheap as the max. It's actually the product of the two bounds, because now you're multiplying, not adding. So for example, if you have nested loops, you're not running one subroutine and then another subroutine after that. You have one loop, and inside you have another loop. So you have one subroutine that gets called, and it calls yet another subroutine inside it. Every time it gets called, it calls the other subroutine over and over and over again in a loop. Well, now you have to multiply out the number of times you called the first times how much the second took each time it was called, and then the product of those two quantities is the overall complexity, because you're doing it over and over and over again, like a nested loop or nested subroutine calls. Okay, how many understand that? Okay, and that's important because when you design algorithms, sometimes you'd have one case versus the other, and sometimes you'd use the sum or the product of the two bounds of the separate things that you're doing. And sometimes you'll confuse the two. That's why I'm very explicitly stating this up front. So to clarify and hopefully avoid future confusion when you actually do need to do this. All right, n to the k is big O of c to the n. So that says that any polynomial is big O of any exponential. Let me repeat that more contextually. Any polynomial, however large, is smaller than any exponential, however small. So for example, n to the 1,000 is big O of 1.01 to the n. That looks almost incorrect when you first see it. N to the 1,000 is huge. I mean, take 2 to the 1,000, 3 to the 1,000, 4 to the 1,000. N to the 1,000 grows very, very quickly. Even for 2, n to the 1,000 is like, much more than a Google. How many can see that? Yeah, Google only has 100 zeros. N to the 1,000 will have about 300 zeros. Or not zeros, but 300 digits. There won't be zeros. And 1.001 to the n goes very, very slowly, sort of. I mean, 1.01 to the 100 is a very small number. Even if you raise it to 1,000, you can do, pull out a calculator and do it, and you'll see. But eventually, this will dramatically overtake that. The exponential will dramatically overtake the polynomial there. How many believe that, or can see it, or okay? If not, try to prove it. I mean, you should probably try to prove this term. Even for extra credit, prove it. It's important enough. At least you should do it once in your life. This kind of comparison. And if you have recurrence relations, which we often have when we design algorithms, especially recursive algorithms, there's something called the master theorem, and I'll just state it here. Well, you can take a look at it. Basically, if you have something of the form T of n is equal to A times T of n over B plus f of n, where f is some arbitrary function, and B is an arbitrary constant, and A is an arbitrary constant, as long as they're bigger than 1, right? You can use that theorem here to solve recurrence relations pretty straightforwardly. And again, this needs to be proven. The book proves it. Maybe you should look at the proof at least once. But then you can just use it. So for example, T of n is equal to 2t of n over 2 plus n. That's a recurrence relation that you typically get from divide and conquer. When you divide some data input set into two pieces, you run recursively the algorithm on both pieces, and then you combine two results, and you do it recursively until the pieces get really tiny, like individual numbers. What kind of algorithm that you've seen before yields this kind of recurrence relation? Merge sort, any kind of divide and conquer that evenly splits the data and recurses on it gives you this kind of relationship, recurrence relation, that if you use this theorem to solve it, you'll see that it's equal to theta of n log n, which is not surprisingly the running time of merge sort. We'll talk about merge sort separately. So it's important to know these kind of relations, recurrence relations, and what kind of overall bounds they, approximation bounds they yield when you work them out. And sometimes it's not so obvious, right? And by the way, there's other ways to prove this, and we'll show you one when you get to merge sort. All right, Stirling's formula is important because it comes up again and again, but it's an approximation formula for the factorial. So if you have all the numbers from 1 to n multiplied out, which is what the factorial is, the Stirling approximation formula for the factorial says that it grows roughly as n over e to the n, or more generally, asymptotically, n to the n is the growth rate, roughly. This is the dominant term here. This is the square root term. It doesn't count for much. And this term vanishes to 0 because it's 1 over n. It's the reciprocal. E here is, of course, Euler's constant, the E that we know and love, 2.71. So, for example, if you take this formula and you try to approximate some other things using it, it often comes in very handy. So because the factorial grows as roughly n to the n, you can compute the log of the factorial, asymptotically speaking, as the log of this formula. And the log of that basically boils down to n log n. And this observation will come up, multiple other times. That's why I'm stating it here so explicitly. The bottom line here is that log of n factorial asymptotically is roughly n log n. It's theta of n log n, actually, both from above and below. And for example, one place this will come in very handy is the proof that sorting has an n log n lower bound. We'll actually use this formula, this approximation formula, and in particular, the thing in red here. We'll want to show that n factorial, the logarithm of n factorial grows as n log n, and that'll be the upper and lower bound, or specifically the lower bound for sorting. The upper bound for sorting comes from actual algorithms like merge sort. Okay, let's talk about data structures. There's a lot of different data structures. And I assume that most of you have seen data structures, worked with data structures, implemented data structures, know different kinds of data structures. So we'll give you kind of a quick summary and then ask you some interesting things about data structures that you may not know and may have trouble actually answering. And that's when we'll really test the subtlety of your knowledge about data structures. Okay, so data structure is basically a technique for organizing information, and there's many, many books strictly on data structures, and this is my favorite dozen books on data structures, but there's many others. It's such a ubiquitous and important concept. And it allows various operations. You got to, of course, initialize the data structure, then you can insert objects into it, delete, you can search it, and many of you have seen examples of that, so you can try to find the min, the max, predecessors, successors, and so on. So you want to enable operations on data structures, and there's lots of different types. Here I'm just listing, my favorite, 100 or so, data structures. The ones in red are ones that are more often used and discussed, and we'll talk about most of the ones in red here, but there's many others. I don't want you to think there's only arrays, trees, and lists, and a couple more hash tables. There's literally hundreds and hundreds of different data structures. There's general categories of data structures. Some are just kind of primitive, like integers and reals. Others are composite. They're made of sequences of these primitives, like arrays or bit arrays or lookup tables or matrices. Some are more abstract, like lists and queues and stacks. Right? They can be implemented in lots of different ways. Some are tree-like. Some are list-like structures with links. And the list goes on and on. Right? And then some are binary trees as opposed to general trees. Right? Some are heaps, heap-like. A heap stores the smallest or the largest object at the top, and the rest are smaller or larger, respectively, than it are in the rest of the heap. And that heap structure or heap properties preserved throughout the structure up and down the heap. Some are specific trees like B trees. Other are multi-way trees. And then there's various data structures that partition space in various clever ways. Some have amortized good behavior like Fibonacci heaps. Right? Most people have not seen a list like this in their life. I'm showing it to you here. Just so you don't think there's only a dozen data structures. There's actually many hundreds. And you can study them ad nauseum. Right? And just to prove the point, I'm listing a few more. Again, the ones in red, we'll discuss some of them or use some of them or mention some of them. They're more useful than others, but some are very, very specific, very specialized. They say they maybe just for graphics or just for video games or for search engines or whatever, and but they're still very specific data structures that are getting a lot of use out there. Right? And there's some data structures are of the hashing type. We'll talk more about that. Some are graph-based, including links, arbitrary links and nodes that connect things. And then there's ones that are even hard to classify in any one of these other categories. And this is just the most common 200 data structures. There's many, many others. Okay, let's start with the basics. Arrays. Array is a sequence of indexable locations. There's a first, there's a second, there's a third. There's like bins or buckets all in a row. Some arrays can be two-dimensional or even three-dimensional arrays. All right, you can have an arbitrary number of dimensions. The computer memory is sort of linear, but it stores multi-dimensional array in what kind of order? Typically, if you have a two-dimensional array, you want to store it in a linear amount of memory, like RAM or even disk. There's a phrase where you store that array, two-dimensional array, in a single one-dimensional kind of storage. It's called row major order or column major order. How many heard of that? Okay, so by the same technique, you can map higher dimensional arrays all into memory, and that's how it actually works. It's unordered, typically, so to add something, you can add to the end of the array, keep adding stuff, but you're not adding it in order. But to search an unordered array takes a long time, because you don't know where the thing is you're trying to search for. You have to possibly traverse the entire array just to find one item, wherever it may be. So the array may take a long time to search, but only a little bit of time, constant time, to add new things to it, if that's the way you want to organize that array. But if you want to keep it sorted, you can do better. And by the way, to find the min and the max at the same time, like to search, because you don't know where the min or the max is. But if you keep it ordered, the time complexities all of a sudden change dramatically. To add something, it takes a long time, because you got to put it in the right place in the array according to the size of the new object. But that means you have to push everything else over to the right, and most of the array could be in that category. It needs to be pushed over. That could take a linear amount of time to do all this pushing once you insert something into the middle of an array, because you want to add it to the array. So that can take a long time, up to a linear amount, where n is the number of things in the array. But now searching speeds up dramatically. And you can use binary search to search a ordered array, and search now becomes very quick, because log is much faster than linear, right? And of course, to find the min and the max also reduces dramatically when the array is ordered, because the min is the beginning and the max is at the very end. And you know exactly where those two things are all the time. So look at the trade-off here between ordered and unordered. Unordered to ordered. The time to add grew from constant to linear, right? The time to find the min and the max dropped from linear to constant. Complete flip on both of these. The time to search dropped, but not as dramatically, from n to log n. That's still an exponential drop, but it's not a complete drop to nothing, to constant. Okay, any questions about any of that? So, simple facts about arrays. Yeah?
Why can't we use binary to add or delete if it's already sorted?
Yeah. So why can't you use binary search and then log time to just add or delete? Fair question. Why can't you add or delete from an array using only logarithmic time? Yeah, because you need to shift everything over. Otherwise, it won't fit. But that's a very good question. Okay, any other questions? All right. So stacks. Stacks can come in last in, first out, or first in, last out. And basically, you push and you pop stuff from the end, from the top of the stack. The bottom of the stack is anchored, and you can only access the end. So you can think about a stack as an access-limited array, or at least that's how you can implement it. Stacks are, you cannot touch the middle. So it's more limited form of access than arrays. And you can think about them as like stacks of trays or plates in your cafeteria, where you can only take the top plate or the top tray, and if you try to remove a tray from the bottom or the middle, something terrible might happen. But you're only allowed to take the top one. Only the top one is accessible in any moment. Lots of applications of stacks, including recursion. When you run something recursively, the compiler keeps track of a stack of frames, of activation calls, and how many know what I'm talking about? Even good, a bunch of you. In compiling, in simulation, in dynamic binding of variables, even in web surfing, when you start using your browser and you keep going through links, and then you pop back up, and then you go some other direction, and there's an implicit stack in your browser. It keeps track of the pages that the long tail of pages that got you to this place, and so lots and lots of uses of stacks all over the place. And why do we bother with stacks instead of just general arrays? Because they're simpler and easier to implement, and easier to implement correctly, and they're more efficient because you only have to touch the end. You don't have to touch the middle, or you don't have to shift anything around like you do with arrays. So it makes it even more efficient. And there's a whole use of stacks in stack automata and push automata, and in theory, stacks get a lot of airtime in terms of analysis of computations, and we'll leave it at that. First in, first out is a queue discipline, right? What you put in gets out, but only later, not right away, right? So you can push and pop in constant time. If you implement it as an array, say, you may have to be a circular array, but that's okay. You cannot access the middle, same as a stack, but you can push in one end and pop out the other. And you can think about arrays as, or queues as basically like lines in your supermarket or lines at a bank, people standing in line. And this line in a bank or a supermarket better be first in, first out. It better not be a stack, first in, last out, or last in, first out. Because people would be very upset if it was a stack, not a queue. Think about it. Those who just came in would be serviced first, and those who came in a long time ago will never be serviced. So, lines in your store and in your bank better be queues and not stacks. But in terms of algorithms, they both get a lot of usage. You get a lot of mileage out of both, right? And they're used in simulations and scheduling and networks and operating systems. And this entire field of computer science, sub-area of computer science called queuing theory. How many heard of queuing theory? It's the analysis of queues and their wait times. And Leonard Kleinrock pioneered that back in the 1960s. I once took a class from him at UCLA. Amazing guy. And it's all about queues. There are different types of queues, the analysis of queues and analysis of average waiting times under various conditions. And queuing theory is getting a lot of usage in network design and scheduling and simulations and other places. Okay, linked lists. This basically gives you links to logical next object on your list. It doesn't have to be right close by to you with the consecutive memory locations or anything like that. It's more logically connected by links to things, and these links could be far away. The whole World Wide Web is one big set of links. It's like a graph. Things connect to other things. Not exactly a list, but just a graph. So a list is a special kind of a graph where each element has only a single successor and nobody points backward. There's no loops in it. You can have lists that are double linked or single linked, right? And both of those have pros and cons. Double links take more storage, but then you can traverse in the other direction, and adding and deleting is a little bit easier. Circular links can go around. Operation take one constant time to add, but a long time to search because it's not necessarily ordered. And deleting given pointers to your successor and predecessor is also very fast. Of course, to find what you need to delete may take a while. But once you have it, it's pretty quick to add and delete to a list. That's why we use lists. You don't have to move everybody one down like you would for an array if you're working with a list. You can just add and delete something right in place, and it takes constant time, so it's lightning fast. Any questions about anything so far? I'm assuming all that is mostly review, but we will ask some interesting questions that will definitely not be review because they'll challenge you. And here's an example. I'm going to give you extra credit for this. So next, we won't solve this today, but I'm giving you a pointer to a list. Let's see how well you understand lists, how really well you understand lists. I give you a pointer to the beginning of a list, and I'm telling you that it can either be a long list with a final element somewhere, or it'll double up and loop on itself, and you don't know which. I'm just giving you a pointer to the beginning of the list. So either it's a long linear list, or eventually loops on itself with a cycle. And I'm asking you for an algorithm to tell me which is which. The pointer that I gave you, does it point to a real long list and that's it? Or does it ever double back on itself and create a loop like this? So it's a yes-no subroutine. Here's the catch. It's got to work in time proportional to the number of nodes in the list. And you don't know what that number is. I'm not telling you what the number is. It could be a list of 3 elements or a Googleplex elements, and anywhere in between, and you don't know which. but it's got to work in time proportional to that. And you can't use any extra space. The amount of extra space you can use besides the list is constant. So it's big O of 1. It's constant extra space. And here's another catch. You cannot modify the list. The list is like on a DVD or a CD-ROM. It's read-only. Or it's a shared list among many users, and they can all look at that data but not touch it, not modify it. They can read it but not write to it. These three constraints make it not trivial. How many have a solution right now? Okay. If you do, that's all right. Make sure it actually works under all these constraints. So about 3 or 4 people have a solution. The other 100 plus people, my gift to you. It'll help you understand lists and algorithms better if you solve this. Any questions about the problem itself? So I'm putting a bounty of extra credit on it till next time. Yeah. You can use 1 extra pointer or 2 extra pointers. That's the constant extra space that you're allowed to use. But you cannot use n pointers or square root of n pointers or log n pointers or any other number of pointers other than a constant number independent of n. Good question. Any other questions about the problem itself? Okay. All right, so I'll just throw that at you. So I showed you a bunch of things that you've seen before that are more or less obvious, just a review, and then I gave you a problem that's not trivial about those things. That kind of tests how comfortable you are really with all these concepts. Okay. So trees. Trees are like lists, except instead of having 1 successor, they can have several successors. At every node, you can have multiple successors, and those are your children. So you can think about a list as a degenerate tree, a tree where every node in the tree has only 1 successor, and that makes it a list. Right? But if you have 2 or more successors, let's say you have exactly 2 successors for every node, now you have a binary tree. But you don't have to be strictly binary. You can have 3, 4, or any number of successors, and you can have multi-array trees, not just binary trees or n-array trees. And trees can be ordered or unordered, right? You can be height balanced or not. Lots of different properties of trees. So height balanced trees, the height doesn't get too much larger than it has to be. And typically it's the logarithm of the width or the logarithm of the number of things in the tree. So those are typically called height balanced trees. Examples include B trees, AVL trees, red-black trees, 2-3 trees, lots of other, there's probably dozens of height balanced tree structures, and careful semantics of how each works and how you add and delete and modify each and so on. But AVL trees and B trees, they typically have like rotations around a node, and when you add nodes, you can kind of rotate around the node, and that rebalances the tree if the balance falls out of whack because you're adding or subtracting to or from the tree respectively. The height can get out of whack in terms of balance, and so you need to rotate around certain nodes to restore balance, to restore the near equal height everywhere. How many seen that before, know how it works, maybe implemented it even? Okay, so it's not news to you, which is good. Typically, because the tree is height balanced, you can add, delete, search, do a lot of these operations in logarithmic time. You never have to dive deeper into the tree than the height of the tree, and it only has to do it once or twice, not an arbitrary number of times, and it works pretty nicely. So an example of how a B tree might work, is like this. Here we're adding some new nodes every time. And once we add these nodes, the tree rebalances, and remember the rebalance operation is this rotation around the node. So whatever we add at the root, this new node like 12 goes down to its rightful place and gets inserted into the tree, and it keeps going like this, and whenever the tree gets out of whack, it rebalances itself and sometimes gets a new root even. And all these operations are kind of this form, at least abstractly, and it works pretty nicely. Any questions about any of that? I'll ask you a question. Why do we want to keep the tree height balanced? Why don't we just let it grow however it wants, in every which direction? Yeah, because you don't want to create long paths in the tree if you can avoid it. Because when you search for stuff, you may have to just dive deep into a tree if it's not balanced and incur a lot of time and expense doing these deep dives, and that'll cost you. So data structures and algorithms, they go hand in glove. They both complement and supplement and enhance each other. So if you have a great algorithm but terrible data structures, the algorithm's not going to be so great because it's crippled by its use of terrible and inefficient data structures. And vice versa. If you have a great data structure that's very efficient, but the algorithm that uses it is terrible, and doesn't use it, but rather abuses it, doesn't use it correctly and efficiently, again, the end result will not be good. So a good design of an algorithm is, or a program, or a piece of code, or even an application in the real world, is good data structures that support an efficient algorithm, or put it conversely, as an efficient algorithm that uses good data structures to run on, and then it's a great relationship. But if either side is, not doing its job, not doing it well, not doing it efficiently, the other will suffer too, no matter how efficient this other thing is. So there was a question back there. Yeah.
Balancing these trees, how do you define balance? Is it those hung at a highest point, or is it the number of nodes?
Yeah. So good question. How do you define balance? So basically, if one of your subtrees is longer than the other by more than one. In other words, sometimes one may have to be slightly bigger than the other by at least one, but you want to keep it at most one. So if it's longer by more than one, you want to rebalance it so that the delta, the difference between the two subtrees, the height of the two subtrees, is back to either equal or one off of equal. Zero difference or a difference of one, but not a difference of two or more. And you can always do that. If you think about it, if something is much longer than the other, you can always chop it off here and hang it off this other thing, and that will restore, the balance will be more restored, more even. Okay? It's like trying to partition a bunch of objects into two boxes. And first you do some random partition, then you see one box has too many objects, then you start moving objects to the other box until they're more or less even, and they may not be exactly even, because you might have 17 objects in only two boxes, so you won't get a 7.5 split, because there's no such thing as half of a node, but you can get a 7-8 split or an 8-7 split, but not a 6-9. That's too unbalanced. So same thing for the heights here. Whenever the height gets too out of whack, you hit it with a rotation. And notice that rotations don't propagate very far. If you start rotating around one node and try to fix the balance around one node, it'll disbalance some other node below it. And then you have to rotate there, and that would disbalance something below it. But this sequence of cascading rotations will not propagate longer than the depth of the tree. And so overall, you only use logarithmic time for these rotations, no matter what happens. And don't get me wrong, it's not easy to get this to work under all circumstances, and if you implemented height balanced trees, there's some special cases and you have to be careful so, things work. So one of the costs you pay for this kind of a scheme, it's harder to program. And there's more room for errors and glitches and bugs, and it's hard to verify that it's correct and make sure it's correct under all circumstances, right? And AVL trees, again, use, what we saw is like a B tree. Now AVL trees but they all work quite similar. The basic operation is still rotation around some node. And multiple rotations occur only infrequently. If you notice that as we added things to the tree, only rarely does the set of cascading rotations go all the way to the root to the leaves. Usually it's the first layer or the second tier, but not all the way to the leaf. Occasionally it goes all the way to the leaf, but definitely not more than that. And that preserves the logarithmic time per addition or deletion. So you can both add and delete and do these rotations in a way that preserves the height balance. And again, the implementation details are kind of non-trivial. You have to make sure it all works, and the code is more complicated than just regular trees where you don't care about balance. But what you win is log n time worst case behavior for both adds and deletes. Any questions about that? All right, and it works nicely. All right, I'll try to finish usually more on time, so we'll stop right there by popular demand. Work lots of problems. You should be working on problem set 1 and work in groups, problem solving sessions Monday nights. Pizza served, my gift to you, and we'll see you next time.
Somewhere in the slides you want to scroll down to like definition.
Oh, you mean today, in today's slides? Okay. Let's see. Here. Yeah.
C should be larger than 1. I think this C should be larger than 1. If it's smaller than 1 and larger than 0, then just go down.
Yeah, you're right. You're right. Okay. Submit that to the class extra credit. Very good catch. The same website, the same email address as everything else. Submit it to the class.